Okay, today I want to talk a little bit more about double and triple bonds, just to finish up yesterday's discussion, and then move on to a little bit new stuff. So, here's where we left off looking at a triple bond for nitrogen, where you'll notice you have each nitrogen bringing in 5 electrons, total of 10, 2, 4, 6, 8, 10. We formed our bond, but we're short 2 electrons here, we're short 2 electrons here. So you shift one pair in to make a double bond. That makes a little better, but you're still short 2 electrons, so you kick that pair in. And now you get down here where we have 1, 2, 3 triple bond. Notice this nitrogen has 2, 4, 6, 8 electrons, so now it's good. The other nitrogen, same thing, 2, 4, 6, 8 electrons, so it's good. So again, you show your triple bond as 3 dashes. If you run, you're doing a Lewis structure, you run short of electrons, make a double bond somewhere. If you still run short of electrons, maybe make a triple bond, maybe make another double bond, but in this case a triple. Now, this is interesting. You might wonder, who cares if it's a single or double or triple bond? Bond's a bond, right? Well, with a double bond, it turns out the bond length is shorter. Notice if you have oxygen to oxygen single bonded, they can measure this and they find out that the bond length is 148 picometers, which means the two nuclei are 148 picometers apart. If you take oxygen to oxygen with a double bond, it's only 121 picometers, so they're closer together, or we say it's a shorter bond length. Triple bonds are even shorter yet, bond length. Why is that? Because remember, each nucleus is positively charged. The electrons between them are negatively charged and pulling them together. A single bond has 2 electrons pulling the nuclei together, so they get pulled a certain distance to each other. A double bond has more electrons, 4 electrons in between, so it's pulling those nuclei harder, and therefore they get pulled tighter together. Triple bond has 6 total electrons, 3 pairs, pulling the nuclei in even tighter yet. So single bond is longer than double bond is longer than triple bond, as it goes there. The more bonds you add, the shorter the bond length gets. Now, they point something out down here that I would have waited and done this a little later, but the model of bonding we're using here, you'll recall from yesterday, is the Lewis model. Gilbert Lewis came up with this way of using dots to figure out who's bonding with who and whatever. The theory works quite well, and we've been using it and getting good answers. However, there are flaws in it, and we want to be aware of where our theories are flawed. The example here they use is the magnetic properties of oxygen. If an atom or a molecule has unpaired electrons in it, those unpaired electrons have magnetic fields, and so the atom will be attracted to or repelled by a magnet. We say that it's paramagnetic. For example, iron atoms have unpaired electrons, so they're paramagnetic. They're attracted to a magnet. Diamagnetic happens when you have all paired electrons. You take an atom or a molecule whose electrons are all paired up, all their magnetic fields cancel out, and so they're not going to be attracted to a magnet at all. Again, we call that diamagnetic. Now, you'll notice with most molecules, I'm going to page back a little bit, our diatomic nitrogen, all the electrons are paired up. Diatomic oxygen, all the electrons are paired up. Bonds a pair, bonds another pair, lone pair, and over here. All your electrons on oxygen are paired up. All their magnetic fields should cancel out, meaning oxygen should be diamagnetic. In other words, not attracted to a magnet. Okay? In reality, if you take liquid oxygen and pour it between 2 powerful magnets, it's going to actually be attracted to those magnets and levitate in the space between them. Won't work with gas phase oxygen because the molecules are moving around too fast. But with liquid oxygen, you can show that it's attracted to a magnet. And so oxygen is paramagnetic. But it shouldn't be. According to Lewis theory, all the electrons are paired up and it should not notice the magnetic field at all. So there's something wrong with our theory. Later in the chapter, if we get a chance, I'll show you briefly an example of a newer, better theory that actually can explain that. Why do we use Lewis model then if it's not entirely correct? Because it works for most stuff. And so just like at other situations, we'll use the theory where it works, and where it fails, we'll go on to something bigger and better. But it's important to realize that our theories are not perfect, and this model that we're using here, while it works very well for explaining a lot of aspects of bonding, it does fail when you get into some very nitpicky, more advanced features. And so we need more advanced models of bonding to deal with that. Now, coming back to single, double, and triple bonds, notice here they show you with nitrogen, the triple bond is shorter than the double bond, which agrees with what I told you before. Here's something else, though, that's interesting. The bond energy, or the bond strength. A single bond is fairly weak, which means it takes not much energy to break that bond. A double bond is stronger, takes more energy to break it, and a triple bond, even stronger yet, takes a lot of energy to break it. Why? Same reason as before. The more electrons you have in there holding the nuclei together, the more energy it's going to take to break that apart. So breaking a triple bond is rather difficult. Breaking a single bond is much easier. That actually becomes fairly important. Nitrogen, remember, is triple bonded. Our air contains a lot of nitrogen and a lot of oxygen. We're breathing in both gases. We need both. We need oxygen to survive, and of course we breathe in the oxygen, and we have specialized organelles that break those bonds and release the energy, and we can use it. We also need nitrogen to make things like proteins. But you're breathing in tons of nitrogen all the time in the air, and your body can't use it at all. You just exhale it right back out. Why can't you use it? Because that triple bond holding the nitrogens together is way too strong. So your cells don't have enough energy available to break that triple bond, even though they love to get at that nitrogen. We actually have in the soil bacteria that are specialized to specifically breaking those bonds and taking the nitrogens and reducing them to nitrates. And those are called nitrogen-fixing bacteria. And those nitrates then in the soil nourish plants, and those plants provide energy to the bacteria in the soil. Without that nitrogen fixing, all the nitrogen in the atmosphere would be worthless to us, and we wouldn't have it available, and life on Earth would come crashing down. So you owe your life to soil bacteria. Now, that's it for the PowerPoint. I do want to go on to some other stuff. Now, I have this in a PowerPoint that I used to use that I'm going to put into the new stuff when I put it together. I'll show it to you here because it'll help the discussion, and maybe I'll upload this to the Google Classroom so you have it. I wanted to compare the types of bonding. Ionic bonding we looked at. You have a metal and a non-metal. Well, up here, metal and non-metal. Weak attraction, strong attraction. All right, great. So sodium wants to give away electrons. Chlorine wants to take them. It's a match made in heaven. So they transfer electrons, get positive, negative ion, and they stick together. Notice there's no ionic bond I can point to. They're satisfied with their electron structures now. They're both isoelectronic with noble gases. The only reason they stick together is opposite charges attract. So the ionic bond is just the opposite attractions. This sodium ion right here, which chlorine did it give its electron to? Who knows? Who cares? Doesn't matter. They're all negatively charged and all attracted to it. So you get this jumbled crystal lattice of ions all sticking together, making it a rather rigid, hard crystal, solid at room temperature. Also notice because there's charges, it's soluble in water, which we talked about back in, I don't know, a few chapters ago. It has charged particles, ions, so it could conduct electricity, as long as those ions are free to move around. In the solid phase, they're not, so you have to either melt it or dissolve it in water first. Now, covalent bonding. Here you got two nonmetals. Both want to take electrons, neither want to give, so the only choice is to overlap their electron clouds and share them, and form this molecule. Notice here you formed a true molecule. This chlorine belongs to that bromine. If the chlorine comes near some other bromine, doesn't care. It's already got its full shell. So you get these individual molecule units that are floating around, bouncing off each other. They hit each other, they just bounce off. They don't stick together because they're satisfied already. Versus over with ionic, where they had opposite charges and they stuck together. So with covalent bonding, you tend to get compounds that are molecules, and those individual molecules bounce off each other with fairly weak forces between them. Now, the bond in here is strong, but the force when this molecule bumps into that one is weak, and so they don't stick together. They tend to be liquids or gases at room temperature rather than solids. Oops. When they form solids, they tend to be softer crystals, not as rigid. So there's that. And they tend to not dissolve well in water, and they don't conduct electricity because, yeah, there's electrons in the bond here, but they're not free to leave and move around elsewhere. Now, metallic bonding, the book doesn't cover it all, and really it's not terribly important until you get to more advanced chemistry. But just real quickly here, what if you have two metals? Both want to give electrons, nobody wants to take. So now what happens is you end up with the metal nuclei and core electrons all kind of cramming together, with the outer shell electrons shown ghostly here surrounding them. The outer electron of this sodium atom is so loosely held that it might migrate over to this atom, then migrate up this way to these atoms. And so you get a sea of delocalized electrons all smeared around through the whole crystal. So that means metals tend to be solid at room temperature, but since they have electrons flowing around between them, they conduct electricity quite well. They're not soluble in water because you don't have opposite charges here for water molecules to grab onto. It's still neutral, just the electrons are flowing around. That's all we have to worry about with metallic bonding. Just looking on the next slide, here I kind of summarize all that. Ionic compounds have strong forces, intermolecular forces, and covalent compounds tend to have weaker forces. So ionic with those strong forces tend to be solid. They tend to have high density because they're crammed together. The ions are crammed together. They tend to be soluble because of charges, and they're good conductors, at least when they're liquid and the charges can move around. Covalent tend to have weaker forces, so they tend to not stick together. They tend to be more liquid or gas. When you do solidify them, they're lower density because there's less force on them. They're often not soluble in water because they don't have charges. Now, obviously, some are soluble in water, like sugar molecules. Water itself has those little sort of charges, so we're going to have to discuss this point tomorrow. And they're poor conductors because the electrons can't go anywhere. Now, the point we're going to work with tomorrow dealing with this is going to relate to a term called electronegativity. I won't make you look at it long because it's ugly, but ultimately we're going to look at how you know whether a compound is going to be ionic or covalent. Right now, you just have to take my word for it. Sodium reacts with chlorine, it's ionic. Why? Because I said so. At the end of tomorrow, you'll be able to look at this weird electronegativity property and decide, oh look, these two elements are bonding together. They're going to be ionic or covalent. So that's what you'll be dealing with tomorrow. For today, the textbook doesn't cover this stuff in much detail at all, so I'm going to make a brief worksheet, maybe 5 questions or so, just so you get a chance to use the knowledge you got here and make sure you understand it. So that's it for today, and we'll move on tomorrow. I'll see you then.